Good afternoon and welcome. We'll go ahead and get started with our second ISR colloquium of the semester. Today, Professor Mark Austin will give a seminar. Mark is an associate professor in the Department of Civil and Environmental Engineering and a joint appointment in ISR. He received a PhD from UC Berkeley in structural engineering in 1985 and joined ISR in 1987. And today, Mark is going to talk about two topics: systems engineering education in ISR, and also his research on ontology-enabled traceability mechanisms. And we'd like to make this an interactive discussion with lots of questions throughout.
Is that fine? Sure. Okay, so everyone knows who I am. Okay, so my original plan was just to talk about the research aspect of things of this new thing called ontology-enabled traceability mechanisms. But Razor said, hey, we've got this MSSE review coming up in November, and this would be a good forum to sort of throw out some ideas on systems engineering education at ISR, and start to think about what to say, what not to say, and so forth. And then part two is the ontology-enabled traceability mechanisms. So what Ray is looking for is some comment on, what was the MSSE like in the 90s? What's happened in the past decade? Where are we today? And what might we want to do in 5 years from now? Okay, so that's sort of what I want to cover. Right, so I thought when I sat down to actually to think about this, I realized a good way of getting started might be to tell a little story. Okay, so the first big question is, how did I actually get involved in this in the first place? Okay, who would be sucking at it? So the person who's responsible for this is Steve Marcus, who came to me in spring of '93 and said, hey, we want you to teach systems engineering design projects. And I'm like, are you kidding me? I have absolutely nothing to do with systems engineering, let alone systems engineering design projects. But completely independently of that, I had this friend, Janine Murphy. And Janine Murphy was working at Hughes. I'd known her about maybe a year and a half, 2 years. Originally, she was working on a proposal, and they were writing this big proposal to NASA, and they were going to build some sort of computer thing that was going to have satellites, and they were going to do environmental monitoring. Okay, and this is her proposal. Okay, this is important. And so they wrote this proposal, and they won. Okay, and she said to me, hey, in our proposal, there's a couple of sections on just a few pages on education for non-science users, and maybe you could come work for us for the summer and help us out. And I was like, well, yeah, okay, but really what I want to know about is, this was the first opportunity for me to actually work at a US company. I'm like, I'll help you with your education, but what I want to do is I want to find out what makes your company tick. And so to me, that means I can ask any question, anytime, anybody, no matter what. And I only have one summer, so I'm going to be pretty ruthless about asking questions. And she knew me pretty well by that stage, and she agreed. Fine. Okay. So on day one of the job, I get there, and at lunchtime, I meet this person in the lunchroom, and I'm like, what do you do? And she says, I'm a systems engineer. And I'm like, wow, we need to talk. So, because I had Dan course. So, she led me to the head of systems engineering at Hughes, who in turn led me to the head of systems engineering at NASA Goddard. And my little summer job turned out to last 2 years. So this was a good deal for her. Okay, so what's the thing? What was going on? So Hughes wrote this proposal to Goddard to create a data and information system And so they started thinking about this project, planning for this data back in '89. They submitted the proposal in '91. They won the award in '92, and they got $600 million for this, which in today's terms is more than $1 billion. Okay, so this was a pretty substantial proposal. And when you sit down to read the technical part of it, they're going to build this data and information system. There are going to be 13 countries that are signed up. And this data and information processing is going to go on from, it's going to start in 1995 and go through 2015. That's the project. And it's interesting because what they want to do is, what do they want to use this data and information system for? They want to answer big science questions about the Earth. So you're going to have, this is where, yeah, so you're going to have, here's the planet Earth. You're going to put up a constellation of satellites. The satellites are going to look down at the data on various aspects of what's going on the planet. They're going to record data, they send it down, and then there's going to be some sort of science processing. So hopefully you can answer questions like, well, how's the Earth changing? What about human-induced actions? What's going on with acid rain? The melting of the ice of the polar caps and so forth. Right. Oops. Too many. Right. So here's a schematic of what's involved. Right. So they want to put up some sort of constellation of satellites. The satellites measure the data. That enables this, and then so the Hughes system. Oops. It's not a very good job. The Hughes system's in here. You have these streams of raw data. You process it. And eventually you can do science, and even at the top, there's even a little spot up here where you might use this data for non-science applications. So the data collection enables science. So this picture is of the hole in the ozone layer over Antarctica, measured over a period of 10 years, and eventually, they figure something else. They realize, it'd be great if we could measure something else, and that drives innovation in the sense that maybe you could develop a new kind of instrument. So you can have some new monitoring, and the thing goes around in a cycle. Okay, so that's the sort of big picture of everything. Oops. Okay, so what can you learn from a company like Hughes? Okay, so because my main goal is that it'll learn. Right. So the first thing is the people at the top were very smart. Very smart. Top 2 or 3 people who are extremely smart people and very strategic in what they do. Much more strategic than in the university. Life science projects involve hundreds of thousands of people. Okay, so that's quite different to a university environment. And think about it. You've got this project that's going to start in 1995, finish around 2015, and it's controversial. Not everybody wants to be measuring environmental stuff. And so here you have a 1995 Vice President Al Gore. This is the guy who wrote the book Earth in the Balance. And who knows how this is going to play out. By 2015 you could have this person in the White House, and you can be absolutely sure the last thing she's going to want is a bunch of satellites looking at her oil companies. They're guaranteed this is going to happen, right? So think about it. If you actually have to manage this program, you have to navigate your way through this system, right? So you have to be. So one of the takeaway is you need to expect that things are going to change, and you have to have mechanisms in place so that you can be adapted. Right. So of course Hughes is working with NASA, and the surprising takeaway there is, okay, sure, NASA's paying Hughes, but in certain cases they don't know exactly what they want. They don't know exactly what they want, and they certainly don't know necessarily how to get there. Okay? So that's the takeaway from a company and sort of sponsor. Right. So what about systems engineering takeaways? So here's the main takeaway. Large-scale science and engineering requires good systems engineering. But that's the takeaway. Okay? Now, the implementation of this is not as simple as what you think. Okay? So the first complication is, hey, this is teams. You've got hundreds and maybe thousands of people working on the development of these systems, okay? And so there's considerable overhead in terms of organizing everything. You may have thousands and thousands, maybe even millions of requirements. You have teams for different purposes because these satellites are going to carry multiple instruments, okay? The instruments are designed to do very specific scientific things. And in the end, somebody has to take all these instruments, integrate them together, and create a working system, okay? So this is actually quite a difficult thing to pull off. And then, as I said, things are going to change. Even before you get into it, you know things. So agility matters, okay? So you have to think about, okay, how am I going to design my system so that my requirements may change, which means that my design may evolve through evolutions. Why do the requirements change? Well, maybe the economics changes, new technologies come along, changes the political sentiment, okay? So, in this proposal, right, now you would think, I read this whole thing, you would think that if you were going to make a data and information system, you would use the World Wide Web, right? The World Wide Web is not mentioned in this at all. Not anywhere is this thing mentioned, okay? So that's how much things can change, right? Then you don't want to wait until you've actually built the system to actually check that it's going to work. So validation and verification needs to be an integral part of the system engineering lifecycle. Now this is actually quite a different thing than the way, say, the Department of Defense does it. So I'm just giving highlights here of just the takeaways. And you want to make absolutely sure the system's going to work, okay? Because you don't actually get to fix things later on. Okay, so one of the takeaways from talking to people who design spacecraft at Goddard is, if you go out on a frosty morning and you try to start your automobile and maybe it doesn't start, you turn the key and it doesn't start. What's the next thing you do? You turn the key again. That's what you do, right? In spacecraft design, you never get to turn the key twice. If it doesn't work the first time, you're dead. Okay? So you need to be absolutely sure that it's going to work correctly, and for that you need formal methods. Okay. Right. So then, back to school. Right. So come back here, I'm going to teach this course, MSSE 623. So here it is over here. So I actually had to go to the graveyard to find this diagram a long time ago. And so the way things work is we have a systems engineering core, and we have a sequence of courses, MSSE 621, MSSE 622, MSSE 623. And so I'm going to teach this MSSE 623 course for the first time, right? And so, and to this day, I am grateful for Hughes because they gave me a mountain of material to bring back to the university. That actually saved me in the first time I had to teach this course. So the next question is, how did it go? Well, okay, so you would think that, okay, if I'm teaching MSSE 623, that, well, what will the students do? They will apply everything they learned in 621 and 622. It doesn't seem like an unreasonable assumption to me. Okay? But when you actually get in there and start trying to do it, you find out that it doesn't really work very well. Okay? So the first big question is, well, why? Okay, so that's the first problem. So the second thing is when you start to talk to the students, okay, about, well, how's it going? You'll get comments like, it was okay. I learned about linear optimization and opportunity cost. But what is systems engineering? And then you think, oh my goodness, man, we are well on the way to screwing this up. Okay? So this is from the students. Then you start to talk to the ISR faculty. So I just put a selection of comments here. So one comment that comes to mind is this systems engineering program is a complete waste of time. Well, thank you. I appreciate that. Okay? And there's a couple of other comments here that are probably even worse. Okay? Pardon? I'll tell you later. Okay. You know, and you get comments like, I'd like to teach an MSSE program, but now it's not a good time. I have this email, and the last 15 years haven't been good either. And then this is my favorite, you can, right there. So you can see, we have our work cut out for us, right? I mean, anybody, I just looked at Gary's report from the final NSF report. Of course, he writes these glowing remarks about how well MSSE is working. I'm like, wait a minute, if you were in the trenches, you would have a completely different story. Okay? So this isn't working, and maybe it can be fixed. Okay? So you can do things to actually fix it up. So let me show you just a few simple things you can do to fix it up. Right. So the first issue was, I'm thinking, this NSE 623, why can't these students do these projects? What the hell are these guys teaching them in the NSE 621 and 622? And then you go and you start to ask questions, like say, why are you teaching topic ABC in this course? And the response I got was, you know, I wanted to teach the topic in my current department, but they won't let me, so I think I'll teach it here. I'm like, no, you can't do this, right? I'm like, who came up with this scheme? So, new approach. If you can't explain how ABC will be used by industries today or in the future, then we're not teaching it. No discussion. Okay? That's just a really basic point right off the bat. Then you can come up with pretty simple explanations of how systems engineering relates to the engineering disciplines and vice versa. Okay? That's not a hard thing to do, but you actually have to do it. Okay? Otherwise the students are kind of left in the dark. And then, okay, then you create schematics to sort of provide a big picture of what systems engineering is all about. Okay? So this picture, okay, so what it is let's see, I've got an organization, requirements, and an engineering system. Okay? And I actually got the idea from this picture. Obviously this came from Hughes. They didn't have this diagram, but just the experience of sort of seeing what people did and so forth, that's sort of what led to this. And the earliest version, in this earliest version of this diagram, okay, I actually got the idea from it from one of my colleagues in civil engineering who was complaining. He said was, why do we have these crappy offices and the people over in the business school have these nice offices? Okay? Well, dummy, that's because the people in the organization here, they keep all the money. Okay, so you see this from Hughes, $1. So the original version of the story was, suppose I have $1, and $1 is fed into think of it like a Coke machine. Well, the guy who runs the organization, he's going to take 65 cents right off the bat. And then here you are over here with your PhD in electrical engineering or whatever. And so instead of getting $1, you end up with about 15 cents. Okay? So there's no way you are going to get rich. Okay? Because the business guy has got all the money over here, right? And then what about this requirements in the middle? Okay? So think about the previous slide. Okay, requirements engineering is BS. Okay? If you go and talk to these people, no. The reason it's not BS is it's a legal document. And as such, this is really important. Okay, so when I was at Hughes, there was a meeting between the top guys at Hughes and the top guys at NASA over 2 sentences that were in this proposal. And to Hughes, the outcome of that meeting being plus or minus $20 million. That's significant. Okay? And so it matters a lot what actually goes into these requirements. Okay, so fine, so you can tell that story. And then you think, well, okay, if I want to be an engineer, what do engineers do? Engineers build models. They spend all their time building models, okay? So, and most of us in this room are engineers in one form or another. If you're a civil engineer, mechanical engineer, electrical engineer, you could go all the way to a PhD basically building models to answer questions about the behavior of something, or the cost, or the assembly, but basically it's questions over here, right? And then you think, well, wait a minute, if building models here is such a good idea, why couldn't you build models in the other areas? And of course you can, right? You could say, well, okay, if I want to do a good job of requirements, I should be able to build models to support the activities that are important in requirements engineering. And similarly, when you come over here to the organization, you would like to be able to build models for the kinds of activities that are important to the organization. And the thing that you need to realize is that what's important to the engineer is completely different to what's important to the guy who's running the company. Okay? So you might be over here worried about the stability of your engineering system. This guy's wondering, geez, have we even got the right project? Are we heading in the right direction? Maybe we've completely missed the mark. Okay?
It's interesting that in some ways it's very simple. So I'm a biologist, and as a biologist, the issues are completely different from the typical engineering issues. But as a systems person, I look at it as a systems engineer, and I go back to the biology and I try to figure out what are the questions and how do I do it. So it's very much like, if you could superimpose anything on that picture that you have there, and that's actually that's kind of cool.
Well, systems biology is systems engineering in the West.
Say it again?
Systems biology, systems engineering in the West.
Yes.
Okay, fine. So, one of the reasons that systems engineering gets in the 90s got such a bad rap from ISR faculty is that there's.
I hope you have everything that you're talking about back before 2001.
It is. I'm getting to your fabulous work in 3 slides.
No, otherwise I'm going to get a real time debate right here.
No. Just hold on a second. Okay? Right. So think about the way this place works, right? Most of the ISR faculty pride themselves in being able to write scientific papers. And what's the quality of science? Somehow is proportional to the density of differential equations on the page, right? They're firmly over here. This is where they are, okay? Differential equations. Right?
Some people do optimization, others.
Well, but you get the story, right? Okay, right, fine. This is firmly planted in mathematics. And so what I'm here to tell you is that there's an equal opportunity for mathematics over here. But the mathematics is different, okay? It's different because in the requirements world, you're interested in communication, okay? And connecting things together.
And
So,
measuring stupidity. And measuring stupidity.
yeah. And making sure things are going to work, right? So the mathematics boils down to the representation and evaluation of logical relationships over very large graphs. Okay? So there are lots of areas of engineering you don't have to really worry about logic much. So, but the mathematics over here is really quite different. Okay? So there's no reason, from a scientific standpoint, that people from ISR couldn't get involved in this whole domain. Okay? This is actually quite a bit more difficult because, if you're worried about strategy, you're thinking, okay, am I going after the right market? You can't kind of build a sensor for that. You have to sort of rely on humans and judgment and things that are a little
But
bit
actually, what I was suggesting is that the biology could fit in the middle, and then it actually has very similar mathematics to the differential equations. It uses the same mathematics.
It's both ways. As a matter of fact, they even borrow the tools we use.
Yeah.
They created something called BioSpice. The system biology is based, there are extensions.
Well, I'm not talking about genomics. I'm talking about
Anything,
any kind of biology.
anything.
Yeah, and it's
We started with a program developed by in 1998.
All right, so the NSF support finished, I guess, around 98, 99 timeframe. 2001. Since
NSF support for you and me, not the ISR. What you talking
I just ISR in general.
about? 97.
Yeah, okay, right. So if you were asked, right, so since 2000, we have worked, John in particular, very hard, okay, to actually
That's not what I meant.
to try and improve things, okay? And so there's a whole lot of things that have happened in the past 10 years to sort of slowly improve the overall quality. So we've got a graph.
I mean, if it wasn't for your involvement with GE, we wouldn't have started on this one.
Probably not.
Right, so that was before the award.
Yeah. So we've had support from, we've got an NSF CRCD project, we've got support from various companies, we've completely redesigned 621, 622, 623, we've got some small amounts of money from the National Technology Foundation, we've done short courses in various places, and these short courses are really important, okay? It's one thing to stand up and talk about various topics here in the NSC 621, 622, but unless you actually go to a place like here and say, hey, this is what we think, you don't actually really know if it's really relevant to industry today. And they'll have no qualms about telling you if they think if they think you're wrong. We had a review panel recently, and recently we became part of the DoD CERT, and as you've seen the posters a lot around ISR, we have this new undergraduate systems engineering course, and the enrollment's 15 this semester. Hopefully we'll fill 30 seats next semester, and then we'll see where we go from there. So there's lots of things that actually happened in the past 10
We
years.
do have to bioengineering students.
Yeah.
That's why.
Yeah.
Okay, right. So Ray's is like, okay, come up with some sort of assessment of the current status. Where do we really sit in terms of systems engineering and the opportunities that exist today? Right. So the one thing, so while we've been sort of slowly doing our own thing, the systems engineering community has really advanced a lot. And systems engineering is a lot more prominent today than it was 15, 20 years ago. A lot more prominent, okay? And so I know Ray's has sent around this slide about systems engineering, the best job in America. So, there's lots of jobs out there now. And one of the things that ISR needs to come to terms with is that we have a lot more competition than we did 20 years ago. And we're falling a bit behind, okay? So, for example, USC and Missouri Science and Technology co-host the Boeing Systems Engineering Graduate Program. And they offer certificates, MSSE-like degrees, PhDs in systems engineering. And the key point is, in this agreement, employees from Boeing or any of their suppliers are eligible to apply. And when we talked to these guys this past summer, they told us they have 3,000 students, okay? So Aaron Dean sees this number, he's going to be all over, okay? But we have competition, right? I mean, we're not the only game in town. There's systems engineering programs at these local universities, and Stevens, which is basically up in New Jersey, is starting opening an office here, right here in Washington, D.C., and they will be happy to take customers away from us. Okay? So, as you know, we recently signed this Crater agreement, and so what's going on in Aberdeen? Well, this is part of the REP program, which is part of the hangover from the Bush administration. There's a net increase of 8,000 new employees going to Aberdeen, and their current target for various forms of graduate education is 1,700 people. And so, of course, Aberdeen is going to look at this, and you can just imagine, right? So they're not going to let us screw this up in a hurry, okay? Right. Okay. So what about, where do we go from here, okay? So we had a meeting, we had various meetings over the summer, and now it's pretty evident that, you can't have a sustainable systems engineering program in a place like this with only a few people being involved. It just won't work, okay? So we need to have a new strategy where systems engineering basically has to become sort of a first-class citizen in ISR. And everyone who's part of ISR should be asked to contribute in one way or another, directly or indirectly. And all of our students need to know what your contribution is. Okay. And so, if you were going to do that, you can imagine creating a little roadmap where you have a core, a systems engineering core for research and education. Okay. And surrounding that core, you can have various application areas, right? So, if I choose something like robotics, okay, robotics can drive advances in system science, but those advances in system science can enable advances in robotics. So you have a two-way thing going on here, just like the Hughes project, okay? And so I've got microsystems, robotics, defense systems, societal systems, and so forth, right? And so this seems like a reasonable roadmap, and it's going to help us too, because we can use something like this to go out and show people on the outside and say, because they already want to know, well, what exactly do you do at ISR? And you can, in just one picture, you can show people what ISR is about. And of course, when Razor saw this, he's like, he's going to like have a 6-foot version of this and pin people's picture on every single part to know where they fit. Okay? And that's actually a good strategy, right? It makes perfect sense. So I'm sure you'll see more of it. Right. Okay, so now let me switch modes and start to talk about the research side of things. So here's one little diagram about the requirements, engineering, and how everything fits together. And so you look at this and you go, wow, there's a lot going on in this diagram. Okay, which part's the most important? And so it turns out that of all the pieces that are on this diagram, it's these links that are really the most important. Okay, they're the pieces that tie everything together. Okay, now, so I remember having a conversation with someone. I can't even remember who it was and where it was, but basically this person was complaining, was saying he or she said, you know, I'm a systems engineer, and my boss does not appreciate what I do. So think about that. Why might your boss not appreciate what you do? Either A, you're a dummy, or B, okay, maybe your boss doesn't understand what you do, right? Maybe they've got no clue. And the reason they might not understand what you do is because these links are missing, okay? Huh? No, this was someone outside of ISR. It wasn't me complaining about Razor. It was someone outside. So I think it's probably someone that got it, right?
I'm saying either you are the dummy or the boss is dummy.
Yeah.
It's not a question of dummy, it's a question of who knows what.
Yeah, who knows? Yeah. But generally, these people here are pretty smart. I mean, they didn't get their information.
They can be in order to do that, they still don't know.
That's right.
I'm talking about common sense.
Yeah.
When you get you that, it's more.
So, of all the things that's going on in this diagram, these links are the most important part. And traceability is the thing that sort of connects things together. That's what it is. Traceability is about. So, right. So one of the things that we've been thinking about in the past, over the past decade, slowly thinking about is, you know, how can you use, is it possible to come up with new ways of actually connecting things together that would be more useful, okay? So we have a general research objective, explore the benefits of ontology-enabled traceability for team-based design and management of systems. And our approach is basically to say, hey, I know I'm going to develop these systems for team-based systems, and they're systems of systems in the sense that you've got concurrent processes going on. But what maybe, you know, rather than starting from scratch, maybe what we could do is look around and find other systems of systems with what infrastructure and take advantage of that. And so the obvious choice is the internet, okay? And especially in the internet too, we have Semantic Web Technologies where they've proposed a whole stack of technologies so that you can, you know, build web pages where you know meaning and therefore provide a pathway to machine communication. That's the general idea. Okay? And so the big question is, can requirements engineering benefit from this stack of technologies? Right. So I had a student, actually about 7 years ago, Scott Selberg, who came across from Agilent, and what he did is create a mapping from requirements engineering tasks, just very traditional requirements engineering tasks, to layers of the Semantic Web Technology. So over here, I have he has his a requirements engineering breakdown, and over here there's a bunch of this is the Semantic Web layer cake. And so you have lots of low-level stuff here, but in here you have things like logic, proof, and trust. Okay, this is really interesting stuff. So you have large graphs of stuff that are going to be evaluated with logic. That's where the logic fits in. Okay? So if I want to do this particular requirements engineering task here, I could use this layer here to help me go where I need to go. Right. And you can do similar things for how you would use requirements. So, what goes on in industry? Okay. So, when I first started doing this, I was lucky enough to meet these people from. I go to the NCOSY conference, and I met these guys from this company called TD Technologies, and they make this very interesting tool called Slate. Okay, and so TD, for a little bit of background, was a spin-off of TI, and they wanted to build tools that would help people do systems engineering. Okay, so this is actually pretty interesting what they've done. They say, well, okay, we're going to build a tool that's going to help you at the very early stages of development. And
These
so,
are actually the same people, just like historical purposes. Several of us here were collaborating in the area of computer-aided manufacturing.
TD.
Yeah,
Yeah.
the same group that we were working with computer-aided manufacturing, a subset spin-off of this back in the early 90s.
So they wanted to build tools that would give you computational support for actually in the very early stages of system development. Okay? And they were pretty smart. They said, hey, you know, when I'm designing a system, there's going to be multiple disciplines involved. There'll be mechanical, computers, software, and so forth, right? And from a system standpoint, what's important is not the details of the, you know, the particular piece of software, but how the software relates to the mechanical part, the interfaces and the connections from one discipline to the next. And so they have this really nice, in their documentation, they have this idea, okay, I have a requirement, I'm going to build some sort of functional hierarchy, functional decomposition for what my system's going to do, and I'm going to represent these things within abstraction blocks, and then I'm going to take these abstraction blocks, and then I'm going to allocate them down to the corresponding disciplines. So here I have electronics, mechanical, software, and now these links are actually going to be connected. And so, how do you connect it? They've got this little notion of a thing called a tram. And so what that means is, if I've got an abstraction block here that does something, and I want to change it, if I've got a tram that says, hey, before you change this electronic, you might want to check with the mechanical guy to make sure that you're not going to break something. Okay, so there's some sort of relationship between the entities in these various domains. Okay? And I looked at this, thought, you know, this is a pretty clever idea. And these guys have a patent on it. You can't build a piece of software with that idea in it. They will come out. Okay? So, and so this little company, TD Technologies, has been bought and sold, I think, at least 4 or 5 times in the past 15 years, and now is owned by Siemens. And it's a very big business. Okay? I remember going to Northrop Grumman, and I know they spent 6 or 7 figures on the software. $20,000 a seat.
No more than that. 150 per day, it's been.
Yeah, millions of dollars in the software. This is a very big business, right? So they've got this fabulous picture, and then you look at their interface, and I'm like, oh God, I'm lost, okay? This just doesn't do it for me. It's not intuitive. You know, someone like, it's a pity Ben Schneiderman was not around at this time, because he would have a heart attack at this. I mean, this is terrible, right? I mean, this is awful. And you think about it, think about the comment. My boss doesn't appreciate what I do. If you show him this picture, it's no wonder he doesn't appreciate what you do. He just spent all his money on this lousy software, and this is the best you can come up with. So I'm like, oh my goodness, surely you could do better than this. Okay. So Scott Selberg, who's pretty astute and a very good programmer. So, and he was interested in systems of systems and semantic web and that kind of thing. And I said, you know, I was complaining about this, and I said to him, why don't you see if you can build something that's just a little bit more intuitive, okay? Just to prove the point that it could be possible. And Scott was really, really into his music school stuff. He spent more time at the music school than he did at ISR, okay? And so he decided, I'll do this. I'll build a toy problem for a metronome. And so it doesn't show up very well on the screen here, but what you've got is a little requirements hierarchy implemented in scalable vector graphics. And here you've got an electrical schematic for a metronome, and here you have like a tabular version of a requirement that's basically just being displayed out of XML. Okay? And I'm like, well, this is infinitely more descriptive than that previous slide. And he coded this in one night. So I'm like, what is the problem with these other people? Okay. Right. So here's the new idea. So I've been thinking about this, and I'm like, well, the way that Slate and Doors and all these other tools work is you have a requirement, and you connect that. You say, well, I have a requirement. How is that requirement going to be satisfied? Well, it's satisfied by this engineering object. Okay? And so you have this dual relationship. If if I'm on the requirement side, I want to know, has the requirement been satisfied? Yes, it's been satisfied. If I'm sitting over on the engineering object side, I want to know, why is this engineering object here? It's here because of this requirement. Okay, so it's a two-way thing. And of course, you have lots of ways that you can make a mess of this. And so I was thinking, you know, maybe you could do it differently. What would be wrong with having a requirement and saying, instead of saying, okay, you know, just give me the answer, why wouldn't you say, what concept am I going to apply to get the answer? Okay, so instead of taking my requirement and connecting it to the object, I could take the requirement, connect it to a design concept, and then the engineering object could just be the implementation of that concept, or multiple concepts, or whatever it would be. Okay? Now, why would you want to do that? Well, this concept is reusable. Okay? And not only that, you could attach rules to the design concept. Okay? And so, if I did traceability this way, I could start to do rule checking even before my engineering design's finished. Okay? And why do I want to do rule checking before the design's finished? Because early validation is the easiest and cheapest to fix. That's the basic idea. Right. And so, in reality, things are a bit more complicated, right? Because, okay, you can't really see it on this diagram. I apologize, I guess the screen's not very good. But this is basically a UML diagram that says, hey, I've got a system architecture. I'm going to describe it with some sort of architectural description. And there are multiple stakeholders that are going to be interested in my architectural description. Okay? And so what this diagram shows is the chain of like cause and effect, stakeholders, design concerns, to viewpoints, to views, and models. Okay? So this is basically a high-level schematic of how things fit together. And the implementation of this is kind of tricky because all of these things in here are many-to-many relationships. So this is, again, you end up with these large graphs that are going to be connected in some fashion. Right. Right. And so, if you have multiple people that are involved in your design, you have multiple requirements, multiple design concepts, and there's going to be some sort of graph in here that's going to explain the dependencies among design concepts and how design concepts map onto multiple objects represented in various levels of abstraction. And in here, if I want to actually represent the relationship between the design concepts, you can create a hierarchy for the various kinds of relationships that can exist. So, for example, one relationship could be the same as. I could have an object in a mechanical system representation and the same object represented in an electrical, and they could be physically, they could be the same thing. Okay? And there are all kinds of ways that things can be related. You might say, well, one thing is inside another, or it's connected to, or it depends on. Those kinds of relationships. So, right. So we decided that we would build a software prototype to see if in fact this could work. Okay. So this was work done by Carrie B, now married, back in 2006. And we have this little software prototype, and I thought, my original plan was, I'm going to do buildings. So that's what I like. Buildings is kind of hard. So then I thought, okay, I'll do a training, because that's easy. Right. So I have requirements, I have an ontology, and we have an engineering system. And so the idea here is the requirements are going to be satisfied by implementing a design concept that's represented in the ontology, and then the various parts of the ontology are going to be connected to the appropriate objects and opinions. So hopefully you know by this point this is the Washington DC system. And so this is how it works, okay? So the idea is that you should be able to interact with the system from any viewpoint. Okay? So here I have the requirements, a window into the requirements, a window into the design concepts, a window into the engineering system itself. So this particular screenshot is, I take the mouse and I mouse over the College Park metro station. Okay? Tell me about the College Park metro station. Well, the College Park metro station, it's a metro station, and it's part of the metro system. And here's the concept. So I have a metro system. The metro system has tracks. The metro system is organized into lines, and the lines are represented into groups. Why do I do it that way? Because it simplifies the navigation. Okay, so everyone here knows that the College Park metro station is on the green line. But if you go over to the College Park metro station and stand on the platform, there is no green line. Okay, it's just a conceptual thing, just to simplify a description of how to get from A to B. That's all it is. Okay, and so you can represent those organizational constructs in ontologies. Now, a transportation engineer would talk in terms of lines and tracks and metro stations, but a mathematician would say, it's just a graph. And of nodes and edges. And if you need to get from College Park to National Airport, I have an algorithm to tell you how to get there. Right, that's what a mathematician does. And of course, the mathematical viewpoint and the transportation viewpoint are linked. And you can do cool things. You can zoom in on College Park metro station. And then how does design rule checking work? You come along, you double click on the requirement, it activates the design rule checking that's appropriate for the satisfaction of that requirement, and then shows you in the engineering system how the thing is actually been satisfied. Right, so Paris, who just walked out the door to go to her class, is picking this up again, and so this is a schematic of what we're going to go with this thing. So the first point is, nobody builds a metro station without trains. We need trains. So this is kind of interesting, right? So, and then trains have a schedule. So we're now trying to figure out how can I model a train. The train itself needs to be modeled as a dot that goes along the line. That's not very hard. How can I model the schedule and the behavior of the trains using finite state machines? So you're going to end up with this network of finite state machines. And then I'm going to have to extend the requirements so that you have, all these requirements here are basically just associated with the architecture of the metro system. But now I want to add behavior requirements. Is it possible to take a behavior requirement and trace it right into a guard condition on the finite state machine? Okay? Now, this is going to be kind of cool because you can have a finite state machine for the scheduler or to time, and the trains start at 5 a.m. and stop at 2 a.m. and so forth. And you could have the trains going down the track, and you could actually show which states are active at which time and how they trace back the ontology right through the requirements. Okay? And I don't believe anybody has this.
Or could this be used to improve the safety of the metro system?
It should be.
Yeah.
You add another metric for another requirement.
Yeah.
Then space distance.
Yeah, that's what we're doing. So this is a pretty general framework, and hopefully we can go along with it.
You can add humans for the incident that happened and ask their behavior for stage for safety and all that. So we get pretty good.
Yeah, I mean, in fact, it occurred to me, Jeffrey, you could even use this in a monitoring situation, where you say replace the transportation system by, it could be like a network of cameras in the city.
Could you use this approach to model a biosurveillance system?
Oh, yeah. Yeah, you could actually, if you think about it, right, I put a camera in a certain location to measure a certain set of things, apply that back to ontology, and then you can use the requirements. Oh, this particular requirement has not been satisfied, and it could trigger some actions.
Because right now the government is very concerned about all these different biosurveillance systems that exist, but there's no, and so it becomes a system of systems, right?
Yeah.
And there's no central,
It's tied together.
there's no central way of monitoring. So,
Well, that's an interesting.
We are working on system engineering research as well. And there has been very much standardization on unit down and memo down and all the stuff, and system and all the stuff, very large system networks, exactly for this problem.
right. So Mark, is the challenge here then,
There are
I
multiple
appreciate
challenges.
what you've done, and I was on Scott Selberg's investment system that you done. So, but is the challenge here like the IT/computer programming part, or is the challenge like how to build these models and link them together? Because like you talk about a model, this finite state machine, but this, that.
Well, yeah, the computer science side of it, yeah, there are challenges in terms of how to actually just implement right? Then there are more challenges in terms of, okay, the ontology side, okay? How do you, suppose I throw away the transportation system, I replace it with a house. A house has an incredible number of stakeholders and disciplines. And look at this room. You have an architectural viewpoint, a structural viewpoint, an HVAC viewpoint, you have a lighting viewpoint, and they're all connected, right? And then when you start to worry about, okay, the dependencies among things, these ontologies could keep on growing. Okay, so I make a decision, for example, if I'm designing a kitchen, I am going to put a microwave in this particular location. Then that means if the microwave's got to work, I need to make sure there's power. And then that triggers something else. And so you have this whole chain of things that are triggered. Okay?
But it gets into this like multi-level modeling kind of thing, right?
Well,
Because
yeah, I
have
mean,
different
you
models
in
and
the end,
different components.
you would put it into multiple layers just to make the thing tractable.
But it's not just the modeling. The modeling is the first challenge. That's where they stopped before. That's why everybody was calling system engineering. I don't want to say the word again. Okay?
Yeah.
All right. So what is the next challenge is to annotate the model's requirements, and as you go at different scales and across models, the logic of these requirements is preserved. Otherwise, you have done nothing. So if I go to do aggregation, I have to preserve some of the requirements. Okay, and then even further link these to trade-off analysis tools. This has not been done. Where it has been done, well, we have a tool in the class that we use which has done for simple problems. But for industrial strength problems, that's open.
Right.
So I can actually go from my SSML parametric diagrams, take the parameters and go to these tools and do multi-criteria optimization. And then when I return,
Right.
I get a valid design. In other words, you have to carry some of these constraints or logics to your multi-criteria optimization or constraint-based reasoning, whatever is your tool that you're using, so that you chase, if you like, in the design of allowable designs, right? In the space of allowable designs. These are the major challenges now. And, you know, we have a speaker coming November 1, 5 to 6:15, and the signing protocol will come from Dr. Martin 5 to 6:15. And if you want to hear the real story where this is going from the industry perspective, please come, because he will talk explicitly on where we are, what applications have been started in this area and what remains. And one of the things that, like Mark talked about, when you go and click on there, right, in the metro, it's called impact. I want to find out if I'm a mechanical engineer and I change something like that here, can I see what else is going to be impacted? Or can the others more importantly see it so they can understand what they have to do and change, right? That's how it becomes interactive. And to do that, right, there's a lot of math and analysis that goes behind it. In a project we did with Dana and Mike Ball back with Westinghouse, we had to use planning and geometric reasoning to try to design some of these things. So that's how I learned systems engineering, from that project and the project we used the hard way. Right? So there are, I mean, a lot of the things that people around here do, they fit pieces of this puzzle, and they can be useful in producing pieces of it. And then somebody has to put it all together. That's where the thing is going, that's why it's called model-based. It's going away from talking about things and doing them by quantitative models and quantitative trade-off analysis and quantitative work, not just talking about the process anymore.
Yeah, so let's say I want to just use system engineering for some project that I have. I'm not necessarily, for example, maybe I'm not speaking for myself, I'm just talking in general. Maybe I'm not interested in research in this area. I just want to use commercial tools and use them for modeling some large system that I'm building. Are there good tools available? And what is the learning curve? And
The learning curve is substantial. Okay, and the tool, I mean, like think about the comments I made about the Slate tool, right, that John and I were talking about. You know, that's a very expensive tool, 20,000 plus a seat, you know, millions of dollars.
is that the state of the art? Slate was when?
Not exactly. They have been in progress exactly because of the costs and the learning curve.
Okay.
I gave a compendium of these three courses, 621, 622, 623. Probably you were there as a student, 98 at MIT, right? To 12 top students in one semester. And they liked the concepts and all that stuff, but they came afterwards with a critique and they said, you cannot teach us the concepts and the software you use all in one semester, it's impossible, even for as good people as we are. So the learning curve was pretty steep. So for that reason, right, they went to SysML, and they're now linking to tools like MathWorks, MATLAB, LabVIEW. These are the object management group now is a subgroup that systematically goes and creates linkages between SysML and things like Modelica, LabVIEW, MathWorks. Okay, so and we are talking to MathWorks to actually create a system engineering workbench at the MATLAB level. So it would be totally trivial, right? And so any engineer who knows MATLAB can do these things, right? Well, at systems of reasonable complexity, because in MATLAB you have an optimizer, you have state flow, you have Simulink, so you can actually link the graphical modeling. And you can do things like communication networks, sensor networks.
But that won't be MATLAB anymore, that'll be MATLAB plus some other stuff.
Yes, it's not, that's right. Actually, if you can, in the class we teach this, we use this magic draw tool, which actually links to MATLAB. So the students, even at the graduates, and even a junior, right? They have to go from SysML, which is an annotated block diagram of an inventor pendulum, do the stability analysis, and then use Simulink and see it actually working in a stable way. That was remarkable because they used 3 or 4 different tools, but now they are integrated to SysML. Okay? So it looks like SysML is like in the center, and other people are linking to this. Very good stuff. The next step we are proposing to do is to link things like ELOG, constraint solver, and simplex to this, so you can actually do very heavy duty optimization, trade-off analysis, and we're going to, as Mark put it, break from the skeleton some of the stuff and read it on this comp, remember the comp technique that we use? We used it with Diana and Mike Ball, discrete version of that to show which constraints were the most non-satisfied. Nobody has anything like that.
That is back to V9.
Yeah, but then I mean, Diana
It's
and
70s.
Mike Ball
But it's
did
still
the
good
discrete
stuff, man,
version of
right?
that. And he had planning and sub-ball planning for geometry and all
Pull
that
it out of
stuff.
the graveyard.
What the aerospace companies want is they want to be able to have these things annotated by geometry. So if I'm an airplane and I say I'm going to change the material here, what parts are going to be affected? Is it the fuel? Is the power? What? So that you can go in and work on this problem, because nobody right will start designing systems from scratch. And then the next big thing that should be interesting to you is that healthcare is getting into this. And real system engineering uses all these tools. Actually, the guy who's coming, that's what he wants to talk about. I bet you. And then IBM bought everything that wasn't in software. They bought Rhapsody, they bought ELOG, they bought Simplex, and they're targeting, enterprise management. And now they come back and say, oh, there is an engineering market for that. So there's a little bit of convergence, and we've been, this time I think it's going to happen, because the software is there, the problems are becoming so complex, and when I say what's going to happen is the engineering is going to happen. It's going to become quantitative, not just as it used to be called papers and reports and processes and all that stuff, which was the blah 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 that people were referring to in the 90s. That's what it's going to be.
Other questions, comments? Yes?
I guess there's just a huge amount of questions about how you map this stuff into OWL and RDF and whatever other logic languages you were planning to do. And that's
Yeah, Paris did lift them, but I figure, if she can, that's a PhD.
No, the semantic web idea that Mark is talking, and he had long discussions with Jim Henry when he was here, it goes to say, okay, if I take the abstraction, but I want to have libraries of pieces of systems or patterns, and I want to pick them up and then try to make a system, can I do that, let's say, by looking over the web? And try to find various pieces of design, sub-design, bring them together, and then have a tool that they will put them in a persistent logic. That doesn't exist right now. The only place it exists is in the MSSE design. Okay? And the next thing we're targeting, the rest is not here, we are targeting to do exactly that for MEMS. Because they have enough components and so on and so forth, you can actually envision that you can reduce design of MEMS to what's called now a compilation process, right? This is what's happening in VLSI. I can go in VLSI right now from an algorithm, mathematical algorithm, to a chip, all by computer. Okay? This is the miracle. Okay, so for what other systems you can do that? And why this is much more difficult than software engineering is that the physical side is what we are in for, because we are engineers, we're not the software engineers. Okay? This is extremely challenging because you have to represent rules of design that correspond to physical and chemical and other principles from the physics of the various disciplines, or the chemistry of the different disciplines. Right? So in other words, you have to have the analog of what Carver Mead and Lynn Conway did for the VLSI, it's with the design rules in mechanical engineering, chemical engineering, and so on and so forth. And unfortunately, these areas, the rules are very, very fast. And biology is the worst, okay, because we don't even know.
Question? Yes?
We're talking about large systems. Of course, the physical aspects of it are very important. That's what engineers really like to work with. The social aspects have their own
Yes, sir.
difficulties, say it that
Right.
way.
Right.
How can you fit those kinds of problems into this system of systems? One part is the physical system, the other part is the social system. And one big system that actually works.
Right? Well, I won't say.
I know, John. I'm just gonna type this.
Point number one, you should not make the fatal mistake that 90% of people make, is use the same models for humans as you use for engineering systems, because humans are what's called anticipatory systems, so you have to allow them free will and crazy stuff and all that stuff, right? But there's a very substantial part of current system engineering that is trying to talk to behavioral people, and try to capture behaviors of people in different situations, model them as anticipatory systems, and include them not as what we call the outside the boundary of the system, but within the system. The most prominent of these areas is social networks via the web. Right? So you have a bunch of folks that they want to use the web to do various kinds of things, e-commerce and other things, right? And you want to do it in a way that's trustworthy. That's a problem where people try to address by this kind of tools. And why this kind of tools? Because you want it to be extendable. You don't want to have it so that if I design 1,000 folks and I have to go to 2,000, I have to do it all over again. Or if I want to add another service, I have to do it all over again. It has to be composable, as it's called. So compositionality, and you heard a little bit of the mathematics that go behind that in the talk by Tripakis about 2 weeks ago. Mathematics are difficult, they're not easy. Of how to take systems and prove that they are composable, and what the heck this means. And when you talk about humans now, it gets even more hard because of the issues I raised. Right? So this issue of trust and trustworthiness, and the behavioral model. This is a very big problem from the Air Force, who is interested in collaborative man-machine systems, where you have agents, robotics, UAVs, and then you have humans. And they want to achieve common goals. How do you organize that? What are the uncertainties that you can capture and model and so on and so forth? This guy is working a lot on games with adversaries, right? This is some of them.
And money too.
Some of them. No, I'm not talking about just playing card games, but in games we have adversarial players and players that play together, and there's a lot of game theory and AI and other things that go into this kind of mathematics.
Most of the things where it's not adversarial. It's complicated. Sorry,
Groups
I have to go.
against groups.
Yeah.